I'm going to forward this in just a moment. I'm sure some of your classmates, if you're missing some of it, you can get it from them, right? Somebody had, at least some people have everything down. Okay, because if you don't, you're not writing, and so I'd hope you're not just depending upon the brain beside you to provide you with all the answers. All right, so I've already discussed the phase symbols, that matter comes in different phases. We've explained solids, liquids, gases, and the last one was aqueous. Okay, we know there's plasma. We're not dealing with plasma in this course. But we've got this other phase symbol we call aqueous, and it just means dissolved in water. So whatever it is that you have, if you had, I think yesterday I said NaCl, sodium chloride. If you had NaCl aqueous, you would know that that was dissolved in water, so you have salt water, basically. Okay? So that's what aqueous means, in water. We started talking about this reaction where we've got methane and oxygen, and they're going to combust. We're going to burn it. Okay? This combustion, this reaction that uses heat, we see the flame of it. Okay? We call it combustion. As a matter of fact, you're going to learn that combustion involves fuel, oxygen, and heat to provide energy for the reaction. And we're going to do a lot of combustion reactions. It's one of the primary types of reactions we're going to be dealing with. But in this case, we have a CH4 molecule, that's methane, okay? Carbon tetrahydride. It's methane. And hopefully you can see now that we have two oxygen molecules. Matter of fact, as we look at this whole thing, we have one methane molecule, right? Is everybody good with that? We have one methane, one CH4 molecule represented up here so far. That one methane molecule is made up of what? 4 hydrogens and 1 carbon, right? So there's a total of 1 carbon in this methane, and there are 4 hydrogen atoms in the molecule of methane. In addition to that, we have 2 oxygen molecules. Each oxygen molecule has 2 oxygen atoms in it, right? Because it's a homonuclear diatomic. So we have 2 oxygen atoms per molecule and 2 molecules for a total of 4 oxygen molecules oxygen atoms altogether. So again, up here we don't have a 1 in front of the methane because 1s are always implied. If there wasn't at least 1 methane, we wouldn't have it on the board. There's got to be at least 1 for it to even show up in the reaction. And if there's more than 1, we indicate that. If we don't indicate how many, it's always assumed to be 1. So we have 1 methane, and we have 2 oxygens. Each methane has 1 carbon and 4 hydrogens, and each oxygen molecule has 2 oxygen atoms. So maybe in your mind you're saying, okay, I've got 1 times, my coefficient here is an implied 1, and my implied subscript is 1. How many carbons do I have? I have 1 times 1 carbons, which is 1. And I'm not going to write that math out for you because I think you can handle it, okay? And I'm not even going to write out the 1 times 4 hydrogens, which equals 4 hydrogen atoms. Okay? And over here, how many oxygen atoms do I have? I have 2 times 2, or 4 oxygen atoms, represented as 2 oxygen molecules. Are we good? Okay. Before I forget it, but I probably won't because I'll probably say it a bazillion times, you get so sick of it, okay? When we get into balancing reactions, you have the authority as a human being to speculate and move around the coefficients in front. You can change the 1 to a 2 or the 2 to a 3 or 3 to a 4 as you try to balance things. You can change that 2 to a 1 or change it to a 4 or change it, okay? What you cannot mess with are the subscripts. Because when you change the coefficient, what you're changing is how much of it you have. When you change a subscript, you're changing what it is. Okay, and we're going to say when we do the balancing, you don't have the authority to decide what molecules are going to be created, but you do have the authority to figure out how many of them can be created. Make sense? So when you're balancing, don't mess with the subscripts. Only mess with the coefficients. Only mess with the numbers in the front. Never mess with the small numbers that are subscripted down. So we talked about burning coal. We said coal is primarily carbon. And that reaction was that carbon plus oxygen reacts to produce carbon dioxide. That's how we would say it, okay? The way we would take that statement, carbon plus oxygen produces carbon dioxide, is to write out the chemical equation carbon plus oxygen produces carbon dioxide. It just so happens, in this case, that this is a true statement and it's also balanced. But when you don't know how many of each thing you need, just assume you need one to start with, and then we'll go from there. It'll make sense in a moment. Okay? So I have one carbon atom and two oxygen atoms to produce one carbon dioxide molecule. Okay? And we said before that that one carbon stays a carbon. There's our O2, produces CO2. We thought of this as there's a process that has to take place. I have one carbon atom and I have one oxygen molecule. That oxygen molecule is going to have to be unbonded because it's held together. And I use the equal sign here to make my graphic easy, but it's a double bonded oxygen for the homonuclear diatomic oxygen, right? That double bond has to be broken in order for the two loose oxygens now, atoms, that's not their natural state, but once they become separated, they then can bond to the carbon to produce carbon dioxide. Okay, so before oxygen starts searching for something to react with, because as a homonuclear diatomic oxygen, it's satisfied. It doesn't want to react. Okay? It has to be broken apart so that it wants to change, and then it finds a carbon, and then carbon finds another oxygen, and now we have a carbon dioxide. So if you think of it this way, the heat from the flame, when we talk about combustion, is the energy that's needed to break up the oxygen molecule to make it available to be two oxygen atoms that can then combine to form a carbon dioxide molecule. All right? So keep that thinking. We're moving forward. Now we're going to talk about combustion of methane. Methane and oxygen. What does it produce? Carbon dioxide and water. All right. So methane, we have already said, is CH4, and oxygen is O2. Again, just the statement. If I said to you, methane reacts with oxygen to produce carbon dioxide and water, you're going to go ahead and assume 1 and 1 equals 1 and 1. You're going to make, here's your methane, here's your oxygen. What's it going to produce? Well, before we can produce anything, we have to kind of break it down. Right? When I look at CH4, what I know I have is I've got one carbon and I have 4 hydrogens. And an oxygen molecule, I actually have 2 oxygen atoms. So we're doing the atom count. How many atoms of each thing do I have to work with? If I have one molecule and one molecule, then in reality what I have is 1 atom of carbon, 4 atoms of hydrogen, and 2 atoms of oxygen. Those are my building blocks. And when I make this reaction, what I'm doing is basically taking the building blocks, which are my reactants, breaking them down into their pieces, and then building them back up as something different. Okay? But what's the key we've talked about already with doing the building block analogy? Am I making or destroying any building blocks? No. Hey, thanks Windows Update feature. Thank you for joining us on YouTube. Not that you're invasive or anything. Remind me in never. Go away. Someday they'll look at this and go, Microsoft, what's that? Okay. So we have carbon, methane that's broken down into carbon and hydrogen, and oxygen that's broken down into oxygen atoms. And the deal is we can't destroy or create atoms. All we can do is rearrange them. So what I'm acknowledging here is I have a structure that's a CH4 molecule. Let me break it down into all of its pieces. And here I have oxygen molecule. Let me break it down into its pieces, to the atoms. So again, 1 carbon, 4 hydrogens, and 2 oxygens. And it produces, we've already said, in other words, the chemistry gods have told you that when this and this react, they produce this and this. They produce carbon dioxide and water. Don't question it. That's the way it is. Boom. Okay. Carbon dioxide and water. If I'm making carbon dioxide, let me make at least 1 carbon dioxide molecule, right? Here's 1 carbon, so it's no longer available. 2 oxygens, they're no longer available. What do I have left over? Well, carbon's used, oxygen used. I've got 4 hydrogens now that are available. What am I supposed to make? The chemistry gods have said I'm supposed to make carbon dioxide and water. Can I? Given my building blocks that are on the board, can I make water? Where? How? I see someone saying yes. How do I make water out of 4 hydrogens. Can I create oxygens out of thin air? Because I need 2 hydrogens and 1 oxygen to make 1 molecule of water, right? Where's my oxygen? Don't have any. So if I need more oxygen, I can put in a request. And I do that by saying, okay, instead of 1 oxygen, give me 2. Okay? 1's not going to do the job because I'm not able to make what I'm supposed to make. So give me 2. You go to mommy, 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 I need more building blocks. Okay, here, have some more oxygen. Now we go through. How many carbons do I have? I've got 1 carbon. I've got 4 hydrogens. And, oh, I've got 4 oxygens now. Do you see that? I requested more oxygen in my reactants. And then I take all my reactants, I break them down into my atoms. 1 atom, 4 atoms, 4 atoms. I know I'm supposed to build carbon dioxide and water. Let me build 1 of each. Well, first I'll build my carbon dioxide. I build 1 carbon dioxide to prove that I can build 1. And then I have 4 hydrogens and 2 oxygens left over. I go ahead and say, okay, I've got 1 carbon dioxide. Let me build 1 of my water molecules. Boom. So I add a water molecule. I use 2 hydrogens and 1 oxygen here to make water. And I have 2 hydrogens and 1 water left over. And I sit there and go, I've got extra stuff. What should I do with it? What would you do if you're trying to make carbon dioxide and water and you had 2 extra hydrogens and 1 extra water left or 1 extra oxygen left over? Make another water. Sure, let's go make another water. Boom, there we go. We have carbon dioxide, and I can make 2 waters, and guess what? I don't have anything left over. It's my perfect recipe, right? We used the analogy before in chemistry that if you made a recipe and you did it wrong, you would make what you're supposed to make and you have leftovers sitting on top, right? Up here, I take my 2 ingredients. I'm supposed to make water and carbon dioxide, but you know what comes out? Carbon dioxide, and I can't make water, so I've got hydrogen sitting on the top of my cake. It's just sitting there. So if you give me more oxygen, I could have made some water here. So you say, okay, I'll try the recipe again, but I'll put it in this combination, and then I make carbon dioxide, and then I can make 2 waters. And there's nothing left over. There's no extra ingredients. And because the count of the atoms on both the reactant side and the product side are the same, we now have a balanced reaction equation. We now have something that we can actually use. Matter of fact, we can use it for a lot of things. We can use it for the rest of everything we do in chemistry. But without it, we're just guessing. Without it, we're making it up. Without it, it's like you react in another class, but not chemistry, right? Because in chemistry, you actually have to know it. I'm being funny. Okay. Thanks for playing along with me. So, the balanced chemical equation. Methane and oxygen produces carbon dioxide and water. That is the formula that we came up with. Here's how you think of it. 1 molecule of methane reacts with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. Okay? If I take 1 methane and 2 oxygen molecules and combust them, I will produce 1 carbon dioxide molecule and 2 water vapors. But here's how we're going to balance it as a process. How are we going to balance equations in the future? Well, we're going to look at the elements. I'm going to go through from left to right, first my reactants, and then my products. I'm going to look and identify every single element that's in there. Now, for those of you that have difficulty remembering that for an element, the first letter is capital and the second is lowercase, because I know there's some of you that want to say that you have 4 CH atoms there. Okay? You did it on the last exam. Okay? Like for the NH3 molecule, you had 3 NHs connected to one another. The first is capital, and if it has 2, the second is lowercase. That's what helps you distinguish the symbols. I look up here and I say, what elements am I looking for? Or what elements do I have? In my reaction, I have carbon. I'm going to have to count out my carbons. Why? Start from left to right. Oh, there's carbon. So carbon needs to be accounted for. What's the next element? Hydrogen. So I've got to count out my hydrogens. And then from left to right, after hydrogen, what's next? Class says oxygen, right. Are there any more elements in my reactions or my reactants? No. Carbons, hydrogen, and oxygen. That's all that I have over here on my reactant side. Now we look over to the product side and look to find out if it's messed up, because I can't change the elements, right? I can't take a carbon and turn it into something else. I just have carbon to work with. Let me look on the product side and find out if it matches. Okay, I'm looking for carbons, got it. Oxygens, got it. Hydrogens, got it. Oxygens, already got it once before. We're good. Nothing new is introduced on the product side. So I'm accounting for all the reactants, and all of those are included in the product. No more, no less. Okay? I can't lose hydrogens and they just disappear. Everything I start with has to be there when I end. Matter of fact, not everything, but the same count of everything. Because I cannot destroy or create building blocks. I can only change their partners, their shapes, and move them around. Okay? God makes the blocks, we get to play with them. We don't have the authority to destroy them or create them. So what we're going to do is count them up. Let's count up on the reactants. How many carbons are on the reactant side? Right, just one, right here on the methane. Hydrogens, good, and oxygens. How many oxygens are in the reactant side of this equation? Sir Jan's-a-lot, how many oxygens are there? 4. 4, right. Why? Because I have 2 sets of 2. Okay? I have 2 sets at 2 per set, or 4 oxygens. Now let's look over on the product side. For carbons, how many carbons do you see over there? 1. Okay, for products then, we have 1. Hydrogens? 4. 2 sets of 2 is 4. 2 sets of 2. Now we get to oxygen. See, oxygen occurs in more than one place, right? Oxygen is part of this structure, and oxygen is part of this structure. So we have to count them all. How many are currently on the board? I have 1 set of 2 and 2 sets of 1, or 4. The question is, then, is this reaction balanced? Yes, it's balanced. How do you know? Because the numbers match. I have 1 and 1, 4 and 4, 4 and 4. I haven't gained anything, I haven't lost anything, I have the perfect recipe. For every 1 molecule of methane that reacts with 2 molecules of oxygen, it will produce 1 molecule of carbon dioxide and 2 molecules of water vapor with nothing left over. Okay? That is the rest of the module. That principle. We're going to do it a lot, but that's the principle. Okay? So what does the balanced reaction equation tell us? It tells us, first of all, what the reactants are. It tells us that methane and oxygen are there. That's what they are going to react. And it tells us what the products are. When methane and oxygen react, they're going to produce carbon dioxide and water. And it tells us what the phases they're going to be in. When I have gaseous methane and gaseous oxygen, it produces gaseous carbon dioxide and gaseous water. And it tells us the coefficients or the perfect recipe. For every 1 of these and every 2 of these, it will make 1 of these and 2 of these. Every single time it will do this. This is one of those absolute recipes. Every single time this reaction happens, these things will be produced in that proportion. And that's the deal. The coefficients in front are actually proportionalities. Now, I've said that 1 molecule reacted with 2 molecules produces 1 molecule and 2 molecules. Good? Fine with that? But since those are proportionalities, it's also true that I can double everything. And I can say 2 of these and 4 of these produce 2 of these and 4 of these. Or I can multiply it by any number I want. 10. 10 of these and 20 of these produce 10 of these and 20 of these. Again, as long as the proportions remain the same. And when I talk about the proportions, we're talking about the atomic or molecular count. The count. not the mass, not the volume, the count. For every one yellow and, blockwise, just think of it that way. We're counting up how many of each building block we have, so how many of each building block can be in our structure at the end. But they're proportional. Because later on we're going to talk about Avogadro's number. 6.02 times 10 to the 23rd. It's a huge number. But if I take 6.02 times 10 to the 23rd of these, 6.02 actually, and if I take 12.04 times 10 to the 23rd of these, it will produce 6.02 times 10 to the 23rd of these and 12.04 times 10 to the 23rd of these, because they always react in proportion to this recipe. But for right now, let's just think of it as molecules, okay? Don't blow your minds right now, because later on what I just said will be easy. Right now, this might be difficult. Think in terms of molecules. 1 molecule of methane and 2 molecules of oxygen combust, they react to produce 1 molecule of carbon dioxide and 2 molecules of water. And the ones are always implied. So it's 1 and 1. Any questions on that? We're good with that? Because we're going to start doing some practices and applications of this. What do we combine everything we just talked about? Could be said this way. The narrative would be, for every gaseous methane molecule that reacts with 2 gaseous oxygen molecules, they produce 1 gaseous carbon dioxide molecule and 2 gaseous water molecules. That's all in this statement right there. So a chemical reaction or a chemical equation is balanced if the atom count of the reactants equals the atom count of the products for each element. What elements are involved? Are they the same number before and after the reaction? If there are the same number for each one of them, before and after, then yes, it's balanced. If there's any mismatches, it's not balanced, and we need to try to balance it. So what does that look like? Determine whether or not the following equation is balanced. 2 molecules of hydrochloric acid plus 1 molecule of calcium bromide reacts to produce 2 molecules of hydrogen bromide and 2 molecules of calcium chloride. The question is it balanced? Every time we ask, is it balanced, we're going to immediately go, what elements are involved in the reaction? From left to right, the first one I run into is, class? Hydrogen. Second one? Someone else? And? Okay. Any others? Check the products and make sure we have accounted for everything. Hydrogen? Yep. Bromine? Yep. Calcium? Yep. Chlorine? Yep. Nothing's left out. We're good. Now we're going to count reactants and products for every one of those elements. Looking at the reactants, how many hydrogen atoms do I have? Does everybody see that? That there are 2. I have 2 hydrogen atoms because I have 2 sets and each set has 1 in it. And hydrogen doesn't appear anywhere else. We're going to be checking that every time. Where else does it appear? Nowhere else. Okay, that's it. We're good. Second one, chlorine. Checking from left to right. How many do I have? Well, I have 2 sets of 1 and no more. So I have 2. Calcium. Calcium is here as 1 set of 1 and no more. And finally, bromine. Bromine is here as 1 set of 2, or 2. Any questions on that process? How I came up with these numbers? Let's do the same thing then for the products. What are the products? By count, hydrogen. Looking from left to right. I have 2 sets of 1 and no more. So I have 2. Chlorine. Left to right, I have 2 sets of 2, so I have 4. If the question is it balanced or not, you're done. You're done. Because you've just found a mismatch. It's not balanced. You can stop, if that's all you're being asked. If you're being asked to balance it, you need to keep pressing on. But if you're just asked, is it balanced? No. Why? I've created chlorine. out of thin air. Okay? I don't have that authority. Therefore, it's unbalanced. It's wrong. It needs to be adjusted. But as we go on, calcium, we've got 2 sets of 1 over here. And bromine, we've got 2 sets of 1 here. Where is it unbalanced? It's unbalanced with respect to chlorine, and it's unbalanced with respect to calcium. It's balanced with respect to hydrogen and bromine. But it's not balanced with respect to chlorine and calcium. And if anything is unbalanced, it's all unbalanced. So is this reaction balanced? No, it's not balanced. Determine whether or not this one is balanced. Okay? Looking from left to right in my elements, there's carbon, oxygen, hydrogen, and more oxygen. We've already got it. Don't need to add it again. Or in fact, I better not add it again because it'll mess up my count. So those are my elements. Let's do the counts, or let's check over here the products. Carbon, got it. Hydrogen, got it. Oxygen, got it. Oxygen, got it. Okay, so we have all the building blocks identified. Now we need to do the count. On the reactant side, the left side, how many carbons do we see? Starting from left to right and go through all the reactants, how many carbons do we have? We have 6 sets of 1 and no more. So I have 6. Oxygen, from left to right. I have 6 sets of 2. Oh, there it is again. And 6 sets of 1. 6 sets of 2 and 6 sets of 1 is 18. Hydrogen. There it is. Okay, back up. I have 6 sets of 2 and no more. We're 12. Now going to the product side, do the same exact thing. The products. Carbon. I have, here's 1 set of 6 and no more. Oxygen. There's oxygen. I have 1 set of 6, there it is again, and 6 sets of 2. 1 set of 6 and 6 sets of 2 is a total of 18. And hydrogen. I have 1 set of 12 and no more. Is this equation balanced? Yes, it is. Because my count for each element, both my reactants and products agree. I have 6 carbons on both sides, I have 18 oxygens on both sides, and I have 12 hydrogens on both sides. This is a balanced reaction equation. I can do more stuff with this one because it's true. An unbalanced reaction equation is false. But this is a true one. So I can do more with it. And the more with it is what we're going to continue to do in chemistry. So this is on your own. And because of the shortness of the day, we're going to press on, okay? But determine whether or not the following equation is balanced. Someone, what's my first element that I need to count up? Okay, somebody else, what's the second?
Hydrogen.
Okay, hydrogen. Someone that didn't respond? Oxygen. Any more? Okay, check the reactants. Does that count for everything? Yep. Products, carbon, oxygen, hydrogen, oxygen. Yep, it's all there. Do the counts. How many carbons are on the left side, the reactant side?
4.
Because we have 2 sets of 2, right? So reactants, we've got 2 sets of 2. 2 sets of 2 is 4. Hydrogens? Somebody else? How many hydrogens are on the reactant side? 12, right. 2 sets of 6 and no more. 2 sets of 6 is 12. And then oxygens. How many? None. 7 sets of 2 is 14. Now looking to the product side and identifying the count for each element. Carbons. How many are on the product side? Correct. 4. Hydrogens? It only appears in the water molecule, and it's 6 sets of 2, which is 12. And oxygen. Oxygen appears in both molecules, right? So we have to count it up in 2 places. In the carbon dioxide, it's 4 sets of 2, and in the water, it's 6 sets of 1. 4 sets of 2 plus 6 sets of 1 is 14. Is it balanced? Yes, it is. So this statement here is a true equation. This is like saying that 7 equals 7. Is that true? Yes. An unbalanced equation is like saying 7 equals 4. Work with that one. Okay, it's going to mess up all your math. So this balanced reaction equation is true, and we can use it for other things. We can also then balance the equations. Because the truth of the matter is, you're seldom going to be asked simply, is it balanced? You're going to be told to balance it. Not just identify whether or not it's balanced, but tweak the coefficients to make it balanced. Now this is where we start having some fun. This is all built on recognizing whether or not it's balanced and then figuring out how to tweak it to make it balanced. So, balance the following. I've got N2 plus H2, so nitrogen and oxygen homonuclear diatomic molecules, forming ammonia. Nitrogen gas, hydrogen gas forming ammonia gas. What's the first thing I'm going to do in my process? Okay, identify the elements. The elements are, hopefully you can see, nitrogen and hydrogen. Is there anything else on the reactant side? No. Is there anything else on the product side? No. There we go. Now we're going to count them up. On the reactant side, how many nitrogens are there? On the reactant side, at nitrogen, how many nitrogen atoms do I have? 2. I have one molecule made up of 2 atoms. So I have 2 nitrogens, and my hydrogen count is the same. I have 2. Okay? Now my product side. How many nitrogens do I have on the product side? Right, I have 1. And how many hydrogens do I have? Very good, 3. So is it balanced? No, that means we need to take more steps to make it balanced. So you're going to continually check if it's balanced, and you're going to keep changing things till it is. So how are we going to address this? Well, the first thing I'd encourage you to do is look to find out where you haven't used something up. Do you see that I haven't used up my nitrogen because I had 2, but I only used 1? So I've got extra nitrogen. Okay? That's the first thing I would recommend that you go to look for. The second thing is if you have used up all your reactants, then if you've got excess product, like if I made 2 and I only started with 1, then go back and tweak the reactants. Again, this flow will make sense after we do a few. Another encouragement, always save atoms of elements. So save elements and homonuclear diatomics for last. Because you don't want to tweak the coefficient of homonuclear diatomic, because if you save it for last, it's an easy cleanup. Okay? It's an easy cleanup, and you'll see that when we do a couple of these examples. So first thing I'm going to look at here is say, okay, I have 2 nitrogens to play with and I only used up 1 of them. I need to use up more nitrogens. How can I use up more nitrogens? I mean, what can I do to this equation to signify that I used up more nitrogens? Add a coefficient to my ammonia, right? Let's make it 2. If I take it and change it to 2, see, I haven't messed with any of the reactants, right? So I kind of got rid of that. But I did mess with a product. And I'm going to encourage you, if you mess with the product side, redo all the products. Or excuse me, if you mess with the reactant side, did I do that backwards? No. If you mess with the product side, redo all the products. If you mess with the reactant side, redo all the reactants. Later on, I think one of the examples, we kind of cascade and do 3 at one time because it's obvious by that point. But right now, just do the whole side again. So right now, I changed this to a 2, so I need to recompute all of my products. How many nitrogens do I have right now on my product side? 2 sets of 1 or 2. And how many hydrogens do I have? 2 sets of 3 or 6. That's right. Is it balanced? No. So we need to do something else, right? What is this saying here? I had 2 and I made 2 or used 2. Here it's saying I had 2 and I used 6. Well, for me to use 6, does it make sense that I have to have 6? Okay, so how do I get 6 over here? put a coefficient of 3 in front of the hydrogen. When I do that, this is what happens. I have to go back now. Since I changed a reactant, I need to recompute all my reactants. My nitrogen count from left to right, I've got 1 set of 2. My hydrogen count from left to right, I've got 3 sets of 2, which is 6. Is it balanced? Boom. This is my balanced reaction equation. Initially, I might have said to you, when you react nitrogen with hydrogen, it's going to produce ammonia. That general statement is true. But more specifically, when you react 1 molecule of nitrogen with 3 molecules of hydrogen, it produces 2 molecules of ammonia. That's a true balanced reaction equation, and we can do stuff with that now. Okay?